right, everybody, it's Dr. Nigro for our last screencast for the notes for our energy and work unit. This one is going to focus on our last topic, which is power. All right, so power is something that we have heard of in everyday vernacular. We tend to think of it in terms of the power company or, superpowers. All right, but power also has a physics definition, and power is the rate at which work is done. All right, so as soon as we see that word rate, that basically tells us that we're going to have time involved. All right, and in fact, the formula for power is W over T. So work divided by time. All right, now don't get this P confused with pressure. That's what we used it for back in chemistry. But in physics, P stands for power. Well, I guess it technically also stood for momentum in our last unit. But in this unit, it's power. All right, now our unit here is going to be a little interesting. All right, work divided by time would give us a joule divided by seconds. All right, but that has another name called the watt, which I think many of you have probably heard of. And it's represented by a capital W as a unit. All right, most people have heard of kilowatts, all right, because that's more often used. But when we talk about power, that unit should come out as watts. All right, another one you might have heard of is horsepower, which we'll talk about a little bit in class. All right, so let's do a practice problem that's going to incorporate everything we have talked about so far. All right, a kid takes her sled, which has a total mass of 40 kilograms, to Narrow Park to go sledding. She climbs to the top of the hill that is 6.5 meters high. What is the sledder's potential energy at the top of the hill? All right, so we know that potential energy is mass times gravity times height. So in this case, 40 kilograms times 10 meters per second squared times 6.5 meters is going to give us a potential energy of 2,600 joules. All right, so that's the potential energy the sledder gained by standing at the top of the hill. All right, she climbs on her sled and zips down the hill with no friction. What was her kinetic energy just as she reaches the bottom of the hill? All right, so all of that potential energy she had at the top has now been converted into kinetic. So her kinetic energy right at the bottom of the hill would be the same value, 2,600. All right, what was her potential energy at this spot? Well, she has no height anymore, so her potential energy would be 0. All right, now what was her velocity at the bottom of the hill? So remember, kinetic energy is 1/2 mass times velocity squared. All right, so if we take our 2,600 joules and we plug in our sledder's mass of 40 kilograms, we can solve for that velocity. So again, multiply both sides by 2, then divide by 40, and finally take that square root, and you're going to find that the sledder was moving at 11.4 meters per second. That's still pretty fast for a sledder, all right, but not as bad as our skier in the last screencast. All right, now let's assume that the snow is actually kind of patchy and the sled encounters 65 newtons worth of friction. If the sledding run was 15 meters long, how much work does friction do? So work due to friction is going to be equal to force due to friction times the distance of travel. All right, so in this case, 75 newtons worth of force over 15 meters of distance is going to give us work of 1,125 joules. So that's how much work the friction is doing to oppose the sledder as she goes down the hill. All right, so what is the sledder's kinetic energy now? All right, so remember, work is equal to the change in the kinetic energy. All right, so in this case, we're going to need to take our initial and we're going to subtract out the energy due to friction. Oops. All right, so the kinetic energy that the sledder has left once we take out the work done by friction is going to be 1,475 joules. All right, so what's her velocity now? Well, we go back to our kinetic energy formula, 1/2 mv squared, and we plug in this time, 1,475 joules is equal to 1/2 40 kilograms times velocity squared. All right, multiply both sides by 2, divide by 40, take the square root, and we find that the sledder is going slower than before, 8.6 meters per second compared to 11.4 meters per second. And this is because the energy that's provided, some of it is being converted into work done by friction. All right, so friction removes some of the energy available. All right, it's not being destroyed, it's just being transformed. All right, and we lose some of that speed. All right, so if the sledder did 110 joules of work over 20 seconds, taking the sled to the top of the hill, what is the sledder's power? All right, so remember, power is equal to work divided by time. All right, so she did 150 joules of work, which she didn't. This is a bad problem. I'm sorry about that. Technically, she did 2,600 joules of work getting that sled up to the top of the hill. All right, but we're going to leave it because that's how it was typed in. Sorry about that. All right, so we'll divide 150 by 20. So this sledder has 7.5 watts of power as part of this motion. Okay. All right, so you can expect problems like this, which are going to incorporate potential energy, kinetic energy, conservation of energy, work, the relationship between work and energy, and then power in the problems that we're going to be working on throughout the unit. Okay? If you have any questions, please don't hesitate to reach out.